Hi everyone, I am Malleshwari with roll number 611955. I am going to explain the topics log transformations and bitplane slicing with demonstration. The general form of the log transformation is S equal to C log 1 plus R, where C is a constant and it is assumed that the shape of the log curve 3 shows that 3 shows that this transformation maps a narrow range of low intensity values in the input into a wider range of output levels. The opposite is true of higher values of input levels. We use a transformation of this type to expand the values of dark pixels in an image while compressing the higher level values. The opposite is true of the inverse log transformation. Any curve having the general shape of the log functions shown in figure would accomplish the spreading and compression of intensity levels in an image. But the power law transformations discussed in the next section are much more versatile for this purpose. The log function has the important characteristic that it compresses the dynamic range of images with large variations in pixel values. A classic illustration of an application in which pixel values have a large dynamic ranges is the Fourier spectrum, which will be at the moment we are concerned only with the image characteristics of spectrum. It is not unusual to encounter spectrum values that range from 2 or higher. While processing numbers such as these presents no problems for a computer, image display systems generally will not be able to reproduce faithfully such a wide range of intensity values. The net effect is that a significant degree of intensity details can be lost in the display of a typical Fourier spectrum. Here the two figures we can see, first one is original digital mammogram and the next one is negative image obtained using the negative transformation, and the previous figure shows an example. The original image is a digital mammogram showing a small illusion in spite of the fact that the visual content is the same in both images. Note how much easier it is to analyze the breached tissue in the negative image in this particular case. And here we can see two figures. First one is Fourier spectrum and the second one is result of applying the log transformation with the value c equals to 1, where c is the constant. And figure shows a Fourier spectrum with values in the range 0 to when these values are scaled linearly for display in an 8-bit system. The biggest pixel will dominate the display. If the expense are lower and just as important values of the spectrum, the effect of this dominance is illustrated vividly by the relatively small area of the image in figure that is not perceived as black. If instead of displaying the values in this manner, we first apply an equation with in this case to the spectrum values, then the range of values of the result becomes 0 to 6.2, which is more manageable. Figure B shows the result of scaling this new range linearly and displaying the spectrum in the same 8-bit display. The wealth of detail visible in this image as compared to an unmodified display of the spectrum is evident from these pictures. Most of the Fourier spectra seen in image processing publications have been scaled in just these manners. And next topic we are going to know is bitplane slicing. Pixels are digital numbers composed of bits. For example, the intensity of each pixel in a 256 level grayscale image is composed of 8 bits. That means only byte. Means 8 bit means 1 byte. Instead of highlighting intensity level ranges, we could highlight the contribution. Here we can see three figures. First one is a aortic angiogram, and the second one is result of using a slicing transformation, and third one is result of using the transformation. And here we can see like figures. You can see A, B, C, D, E, F, G, H figures. Like here, those figures shows, first figure shows an 8-bit grayscale image of size pixels, and the second one is through one 8-bit planes, one through 8 with bit plane, one corresponding to the least significant bit. Each bit plane is a binary image. Figure A shows an 8-bit grayscale image and figures. Figure B through 1 are its 8 1-bit planes with figure corresponding to the lowest order bit. Observe that the four higher order bit planes, especially the last two, contain a significant amount of the visually significant data. The lower order planes contribute to more subtle intensity details in the image. The original image has a gray border whose intensity is 194. Notice that the corresponding border of some of the bit planes are black, while others are white. Pixels in say the middle of the lower border of figure A, the corresponding pixels in the bit planes starting with the highest order planes have values 11000010, which is the binary representation of decimal 194. The value of any pixel in the original image can be similarly reconstructed from its corresponding binary valued pixels in the bit planes. In terms of intensity transformation functions, it is not difficult to show that the binary image for the 8th bit plane of an 8-bit image can be obtained by processing the input image with a thresholding intensity transformation function that maps all intensities between 0 and 127 to 0 and maps all levels between 128 and 255 to 1. And here we can see three figures. These figures are images reconstructed using bit planes 8 and 7, and second one is bit planes using 8 and 7 and 6, and the third figure is using bit planes using 8, 7, 6 and 5. And decomposing an image into its bit planes is useful for analyzing the relative importance of each bit in the image, a process that aids in determining the adequacy of the number of bits used to quantize the image. Also, this type of decomposition is useful for image compression, the topic of chapter, and in which favor then all planes are used in reconstructing an image. For example, figure A shows in previously the figure A shows an image reconstructed using bit planes 8 and 7. The, the reconstruction is done by multiplying the pixels of the nth plane by the constant 2 power n minus 1. This is nothing more than converting the nth significant binary bit to decimal. Each plane used in multiplied by the corresponding constant, and all planes used are added to obtain the grayscale image. Thus, to obtain figure A, we multiplied bit plane 8 by 128, bit plane 7 by 64, and added the two planes. Although the main features of the original image were restored, the reconstructed image appears flat, especially in the background. This is not surprising because Two planes can produce only four distinct intensity levels. Adding plane 6 to the reconstruction helped the situation. As figure B shows, note that the background of this image has perceptible falls. Countering this effect is reduced significantly by adding the fifth plane to the reconstruction. As figure C illustrates, using more planes in the reconstruction would not contribute significantly to the appearance of this image. Thus, we conclude that storing the four highest order bit planes would allow us to reconstruct the original image in the acceptable detail. Storing these four planes instead of the original image requires 50% less storage, ignoring memory architecture issues. Thank you.